Hello everyone, welcome back. Today we are going to continue our discussion of transformations of various different types of functions, and we're also going to review factoring and describing graphs. So we will start with factoring. So we have an equation here, x squared plus 10x plus 24 equals 0, and we want to use factoring to help us solve this equation, right? So we're trying to find values of x that will make this thing be true, and we're going to use factoring to do it. All right, so I'm going to start by drawing my box. So remember, we use the box and diamond method to help us with factoring. So I draw a box. I'm going to divide it into 4 compartments, and I'm going to go ahead and set up my diamond right here next to it. Okay, so to begin factoring, we take the first term, right, the x squared term, and we place it in the upper left-hand box. We take the constant term, or the term on the end here, the 24, and it's going to go in the bottom right-hand box. The 10x is going to go in the bottom of our diamond, because that is what our 2 remaining boxes have to add to. And then to get the top of our diamond, we're going to multiply this first diagonal. So if I multiply 24 and x squared, I get 24x squared. So I need 2 numbers that multiply to 24 and add to 10. So again, you might have to think about this. You might try out several different combinations before you find the right one. The key is not to give up. All right, so the 2 numbers that are going to work here are going to be 6x and 4x. 6 times 4 is 24. 6 plus 4 is 10. So I will fill in my diagonal with those 2 numbers. Now I work on the outsides, right? So I know I'll have an x and an x, right? Because x times x is x squared. And then x times 4 will give me 4x, and x times 6 will give me 6x. And now we can see our 2 factors on the side of the box. So we'll have x plus 6 times x plus 4 equals 0. So this expression, or this quadratic, was replaced by its factored form over here. It is the same exact equation. They represent the same exact parabola. But this is much easier to solve because I can use the zero product property. So I can take this x plus 6 and set it equal to 0, and then solve by subtracting 6 from both sides. So I'll get x equals negative 6 as one of my solutions. I'll do the same thing with x plus 4, and then subtract 4 from both sides, and we find that x equals negative 4. When you go to enter your answers into MyOpenMath, you'll state it like this. You'll say x equals negative 6 and then comma negative 4. So you separate your 2 answers with a comma. You do not need to put parentheses on this. Even though it looks like an ordered pair, it does not represent a location on the graph. It represents 2 solutions to an equation. All right, the next problem we're going to review here is how to describe a graph. We haven't seen one of these in a while, so it might pop up on the quiz this week, so wink, wink. You might want to make sure that you can identify these things from a graph. Okay, so we have a rational, or a square root function going on here, and the first thing they want to know about are the x-intercepts. So you'll notice the x-axis is down here below the function, and since this function continues off to the right and keeps going up forever and ever, it will never hit the x-axis. So we're going to say for x-intercepts, d and e. Right? The y-intercept is the location where the graph is going to cross over the y-axis. So you'll notice here it crosses over the y-axis at this location, and this one doesn't cross on a nice number, so if I count up 1, 2, 3, it's just below the 3. So I'm going to describe the y-intercept as 0, and let's eyeball it to 2.8. Okay. Make sure you enter that as a coordinate pair, right? So x comma y, complete with a set of parentheses. The maximum is the highest point on the graph. So if I were to ride this like a roller coaster, or if I were to jump on this graph and try and climb to the highest point, we would keep going up and up and up and up, and this arrow on the end would indicate that this function keeps going on and on forever. So it's never going to stop going up. That would indicate that there is no maximum. So we would say d and e. The minimum is the lowest point on the graph. So again, if I were to get on this and start walking downhill here towards the left, I would stop here at this point. So this becomes the lowest point on the graph, and this has a coordinate. So if I start at the origin, I'm going to go 1, 2, 3. So we have an x-coordinate of -3, and then I would go up 1 to get to that point. So we would be at -3, comma 1. That's where the minimum is located. Domain. All right, so domain is essentially a way of describing all of the x values that a function can be. All right, and the way that we do that is we look at a function and we say how far to the left can we go and how far to the right can we go. Okay, so if I'm getting on this function and I start traveling off to the left, it stops right here. Right, so if you can kind of think like this is as far left as it goes right here, and that's as far left as -3. So I'm going to say this goes from -3 up to, and then if I were to travel off to the right, right, how far to the right does it go? Well, this arrow tells me it never stops going off to the right. So it goes from -3 to infinity. We can actually get to the -3, so I'm going to put a square bracket on the -3 and a curved bracket on the parentheses. We will never get to infinity. Okay, so remember, square brackets are for numbers that you can get to, which we can. That's why they have a closed dot on the end. And the curved brackets are for numbers that you will never get to. All right, so infinity is one of those numbers. All right, the range is a way of describing all of the allowable y values. And the easy way to find that from a graph is to ask yourself, how low does the graph go and how high does it go? So again, if I were going on my function and I were going to walk downhill, I would walk downhill to this point and then look at where I'm at on the y-axis. Okay, so we are at 1. So my range goes from 1. That's as low as it will go. And then I would start walking uphill to see how high I would go. And according to this arrow, it'll never stop going up. It'll keep going up forever and ever. So the range goes from 1 to infinity. We can get to the 1. We cannot get to the infinity. All right. The line of symmetry would tell us if there was a place where we could fold this graph in half and get one side of the graph to land on top of the other. All right, so it's that fold line that cuts your graph perfectly in half. For this particular function, there is no place where that is going to happen. All right, so for this one, we would say DNE. All right, guys, so let's get back to transformations of graphs. All right, so again, this is our table that kind of summarizes all of our very important information. We have our parent functions here, the graphing forms for each of the different types of functions that we discussed the other day. And essentially, you're going to see 3 types of problems. I might give you a description and ask you to write an equation. I might give you an equation and ask you to give me a description. Or I might give you a graph and ask you to write the equation for me. All right, so we need to be able to go from all the different representations from one to the other, whether it's a description, a graph, or an equation. All right, so let's take a look at this first one. In these ones, I'm giving you a graph, and I want you to write the equation of this graph. And we actually just saw this one above. This is the one that we described before. And if you recognize the shape of the graph, right, if I were comparing it to one of the 4 shapes that I see up here, I would say it looks the most like this one, which is a square root function. And what that means is I'm going to be writing an equation that looks like this. So I'm going to write that down. That's my blueprint. Right? So I'm going to say y equals a square root x minus h, and then that plus k, be very careful, that goes outside of the square root. All right? So now I need to start looking at my graph for my clues. I need to find a, h, and k. Right? So the a value, if you read the instructions, you would see that it said the stretch factor is 1 or -1. So if I look at the graph, I notice it has not been reflected. Otherwise, this curve would be opening down in this direction, but it's opening up and to the right. So this has not been reflected, which means that a is just going to be a regular 1. Now the h value and the k value can be found by using the locator point. Okay? And remember, our locator point is this point, which starts on the origin at 0, 0, right? So before it's been moved left or right, the locator point starts at 0, 0 for the square root function. So on our graph, our square root function started here, but ended up over here. And we can use the difference between those 2 points to help us figure out what the horizontal and the vertical translations were. So horizontally, this graph moved to the left, and it moved to the left 1, 2, 3 units. So I know h represents my horizontal movement, and to move to the left, I need a +3. So x plus 3 will go inside of the square root. I also notice that it has moved up 1. And to move up 1, I need my k value to be a plus 1. K represents the vertical shifts. And that completes my equation. I now have all three pieces. I have the stretch factor, the horizontal shift, and the vertical shift. All right, let's try it again, this time for a cubic. All right. Okay. So again, if I knew that it was a cubic because I looked at the shape and I compared that shape of the graph to one of the shapes that are up here. And I noticed that it resembled this one the most. Okay, so that is a cubic function, which means this is my blueprint. That's what my equation is going to look like when I'm done. So I'm going to write that down. I'm going to say y equals a parentheses x minus h cubed plus k. And then I'm going to start looking at the graph to find my three pieces of information. Okay, I'm going to start with the a value. Now, I look at this and I have to ask myself, has it been reflected? All right, so one of the things that I do is I come up here and I remember this is my parent graph. This is what it looks like before I've done any reflections. So normally it opens up to the right. Okay, if it had been reflected, it would be opening up to the left. It would be opening up over here. Okay, so I'm going to take a look at my graph here, and I notice that it's not opening up to the right of the locator point, it's opening up to the left. So this would be something that has been reflected. And I want to demonstrate that a little bit more on the Desmos graph. Okay, so I have a cubic function here, and you'll notice I just have a regular 1 in front of the parenthesis here, and you notice how it opens up to the right of the locator point. Okay, now if I throw a negative in front of it, watch what happens. Notice that this part that was going up this way is now going up and to the left. And if I get rid of that negative, it goes back. Right? So Desmos is a great way to experiment and play around with these functions so you can see what does it look like if a cubic has been reflected versus not reflected. And then you can go to your graph and compare that to your own. Right? So if I look at this one, it's opening up and to the left here. So this would tell me that it has been reflected. All right, so when I write my equation, I'm going to say y equals -1. I have to put a -1 there to get that reflection. And then I look at the locator point. So remember, it always starts at 0, 0, so I can use that difference to tell me which direction it has moved. Horizontally, it moved to the right, 1, 2, 3 units. So to move to the right 3 units, I need an x minus 3 cubed. And then it moved up 2 units, so I need a plus 2 on the end. All right. These last two problems ask us to write the equation of a function given a description. So I describe the function to you, you have to write the equation. So the first thing that they're going to tell you is the shape. So notice that this one is a quadratic. This one's not on our table up above. This is one of the original parabolas that we've been talking about for the last 2 weeks. So we should know that graphing form well. Y equals a times x minus h squared, because it's a quadratic, plus k. So we know that our equation is going to look like this when we're done. So I'm going to go through the clues and I'm going to find my stretch factor first. So the stretch factor is 5. It has been stretched by a factor of 5, so I'm going to replace the a with a 5. Then we say x minus h, so I'm looking for my horizontal shift. All right, so that's going to be here in clue 2. It says it's been shifted to the right 2 units. To move to the right, we need an x minus 2 and then squared. Don't forget your exponent. And then I need my k value, so I'm looking for a shift up or down. So it has been shifted up 5 units, and to move up 5 units, I need to change k to a plus 5. And that completes my equation. Okay, so for this last one here, this one says it's a rational function. So a rational function looks like this. So I'm going to set up my blueprint. And then go find my clues. I'm going to start with the stretch factor. So down here in clue 4 it says it has been compressed by a factor of 0.7. So I'm going to say y equals 0.7 over. The next thing it wants to know is the horizontal translation. So I'm looking for something that has moved it left or right. Now it doesn't specifically say that it has been moved left or right, but it does tell me where the locator point is. So if the locator point is at -7 on the x-axis, that means it had to move to the left. So to move to the left, I need an x plus, and to move to the left 7, I need an x plus 7. Now, the vertical translation is also given to us in the locator point by looking at the y-coordinate of the locator point. The y-coordinate reveals to us that it has been moved down 4. So I need a -4 on the end. And that completes my equation. All right, guys, have a great day. Good luck on the practice problems.